Okay, so the next talk is an experience report about formally verifying a high-performance microkernel. And the paper is Gerben Klein, Philip Darren, and Kevin Elphinstone, and Gerben is giving the talk.
Thank you. I'd like to start by adding a challenge to the last talk for mixed imperative and functional programs. That would be operating system verification as well, additional to compiler verification, because that's what I'll be talking about, and that's basically what we did kind of sort of as well. Not as, we didn't try to achieve maximum automation. Instead, we tried to prove a particular big program correct. Okay, so it's a short slot, and I tried to put the most important bits on the first slide. So yeah, that's pretty much the message. So we took one particular operating system, microkernel. It's about 8,700 lines of C big. We proved in Isabelle Hall that it's functional correct. And as always, there's some fine print. I'll show you the fine print later, but we think it's a pretty strong statement, actually. I've tried to visualize how big 8,700 lines of code is. And so that's seL4. That's the function call graph of it. So each dot is a function, and there's an arrow between two functions if A calls B, basically. And you can see, well, it's a microkernel. It's really messy code. It's highly optimized. There's no modularity in it. Everything depends on everything else, pretty much. And that's actually by definition. Microkernels are like that. If there's a feature that's nicely modular and that you could take out of the kernel, then you would. That's what a microkernel does. So it provides really minimal services. It tries to it gives you threads, it gives you communication, message passing between threads, it gives you virtual memory, interrupts, and capabilities for access control. And that's pretty much it. These are the basic abstractions from which you then build things like device drivers and higher level operating system principles. Okay, so much about seL4. I promised fine print, so here it is. Bug is defined here as a deviation from the abstract formal specification. That's a bit narrow than it's a bit more narrow than what a normal programmer would say. But in program verification, that's usually what you care about. Deviations from your specification. What we proved is functional correctness in the sense above. So it's a very classical refinement statement. So we have an abstract formal specification A, it's operational. It has abstract states, and it says for each kernel input, for each event, for each trap instruction or each interrupt, for instance, what can happen and what is the next state. And we prove that the C code parsed into Isabelle formally refines that on the level of the operational semantics. The proof is not directly on the operational semantics. We lift this to Hoare logic and so on with a quite large framework, but the proof statement, this theorem, is about the operational semantics of C. Okay, so this is all quite nice. What are the assumptions? Well, it all basically goes down to the level of C. So everything that's below C, we don't prove at the moment. So we assume that the compiler and linker are correct. There's actually a very exciting project by Xavier about proving compilers correct, and I've just heard that there is one for the ARM platform. So the ComSert project has a backend for the ARM platform now, and as soon as I get home, I'll actually try this out on this, because then we can remove that assumption. It's not quite that simple, but yeah. We also have to assume that the hardware works as specified, just to get the operational semantics of C going. The assembly code as well, that's below our level of abstraction. And here's a bit where you could say, well, maybe not. It should be verified or maybe not. So we, at the moment, leave out low-level cache management and the virtual memory cache, the translation look-aside buffer. Basically, what we do is we assume that flushing the cache doesn't do anything in the operational semantics of C, which is correct if you use these flush instructions at the right position in the code. If you don't, your operational semantics of what's actually happening on the machine might be quite different from what you see on the formal side. So we have to basically assure by testing or by looking at it carefully at the few places where we need them that we use them correctly. And we leave out the boot code that runs once initially to boot up the machine and that loads the kernel and sets up the initial page tables. So what's really verified in the end is not the whole 8,700, but 7,500 lines of code, so minus that. But that's it. So that's really the statement. Okay, so operating system verification. Why am I here really at ICFP? And Well, the answer is in the proof. If you look at this picture here, this is trying to show how the architecture of the proof looks like. At the bottom of this specification stack here, we have the C code parsed into Isabelle. On top of that, we have a very detailed high-fidelity executable model, so sort of a low-level design, you could say. On top of that, we have this abstract specification that we prove correctness towards. And on top of that, we're currently working on a nice little security model that has a small confinement theorem. The confinement theorem is already proved. What's not proved yet is the connection between the security model and the abstract operational specification of the kernel. Okay, so the interesting bit for here is this. The executable model is not written by hand in Isabelle, as you would probably normally do in a verification project like this, but it's generated from a Haskell prototype. So that's our main connection to functional programming here. Of course, all these specifications are written in a functional programming language as well. So they're written in Isabelle Hall, and that's basically, a simply typed lambda calculus, which is completely normal in theorem prover. So if you use ACL2, you would have Lisp here. So that's not really the connection I mean. What I mean is we have this completely standalone program, a prototype, that not the verification team wrote, but that the OS designers wrote, which is a separate group within NICTA where I come from. And they didn't want to learn theorem proving at all. They didn't want to do specifications. They wanted to do programming. And they came up with the idea, let's use Haskell instead. That's, at least it has a clean semantics, and we play with Haskell, and you see what you can get from that in terms of specification. So 3 years ago at the Haskell workshop, we showed a slide that's pretty much this one. It explains how this Haskell prototype fits into the process. So designing and specifying a microkernel is really, it's a whiteboard activity, right? People meet, people discuss, have ideas, and when they agree or disagree on something, someone goes away and, in this case, writes it down as code in Haskell. And the nice thing here is that you can try it out. You can run it, you can run user-level binaries on top of it, and see, are the features that I just implemented, is the design that I just did, is it what I want? And you can do that without worrying about high-performance C implementations at the moment yet. And you can do that without worrying about real hardware yet, because it's actually quite hard to get the first version of such a C implementation running. The nice thing for us, for the verification guys, is that Haskell has a nice clean semantics, so we can, in this case, we generate Isabelle Hall code from it, a specification, and we get our first executable formal specification of the kernel without doing any additional work. And we can start proving stuff about that specification, already giving feedback into the design, saying this is too hard for us here, or you can, if you have an additional property here, you can optimize there, and so on. And yeah, that's pretty much it. That's the connection. And Haskell sort of was the driving motor, the engine of this cycle. So you iterate this cycle in the top left corner. We did that for, I don't know, at least a year or maybe 2, until it sort of stabilized. And then we implemented the C version of the kernel manually. And we also started to formulate a more abstract specification of what the kernel is. Something that uses, non-determinism and infinite sets and lists and trees and so on, instead of pointers and an explicit model of the heap that we did in Haskell. Just to contrast this with normal development processes, this is what the kernel guys would usually do. They would, meet at the whiteboard, implement it in C, hack at it until it performs really well, because that's what they care about. Performance is everything. Until they're done. This takes quite a while. This is actually a hard process, and they were quite happy to be rid of this initial C implementation step. So it's them that liked Haskell a lot. For us, for the verification side, if we had done this alone, we wouldn't have bothered with implementation too much. We would have had a discussion, maybe not even a low-level design discussion, but first a high-level design discussion, then write the executable spec, and then write the C code. In the end, well, by now I'm pretty convinced that we would never have gotten anything that performs in any, within even an order of magnitude of what this kernel now does. So this is what we have. And yeah, so the main thing is you can validate your design early. And you have an easy case, an easy path to both C and an abstract specification. So this was the story in 2006. What we had there was we had this process. We went through it a couple of times. We had a very initial version of the abstract specification, very initial version of the C implementation. We didn't have any proofs yet. So now, 3 years later, we do have the proofs. And the question is, what is the influence of this choice of Haskell and then generating Isabelle from Haskell onto the proof? So the proof was in 2 big steps, upwards and downwards. So first upwards. One thing I should mention is the abstract spec was written after the Haskell prototype was there, and we were, of course, we knew it, we looked at it, and we used some of the structure in this specification, and we used especially the monad feature that it used all over the place. So it's mostly imperative code mixed with some functional code, so very much like in the last talk. And yeah, I don't think we would have used monads in Isabelle directly. So we had to, produce a formalization of the state monad, put a whole logic on it, did a refinement calculus between these things, have invested quite a bit into automation, and well, in the end, I think it worked quite well. The interesting bit, though, is it didn't feel like a design proof at all. This was supposed to be a proof between high-level and low-level design, but it wasn't. It was really big, and about 110,000 lines of proof script. So this is manually written, machine-checked, and it's from the degree of automation, I think it's sort of comparable to what we just saw, maybe a bit more automation even than that, because we had specialized tools for specifically this program. What can I say? Well, so it was much larger than we expected. But all the interesting reasoning was here. So the deep semantic reasoning about termination, about why algorithms work the way they work, about how data structures are laid out, why they work, and so on, this all happened here. And if you look at the proof, you see that only 20% are really spent on this arrow going up and down, and 80% are really proving properties invariants about each of the specifications on the abstract and on the executable level. We found about 150 bugs in each of these specifications during that process. Most of them were very simple, banal things like copy and paste errors or just simple typos. So on the order of about 15 were really actually deep algorithmic problems that we had to meet about and talk about and change the design a bit. So yeah, that story actually is very similar on the next level, where we found 160 bugs. But let me back up and say what the influence of the Haskell proof was there. Basically, the first step took much longer than we expected, and the second step took a lot less than we expected. So when I initially set out and wrote the project plan for this, I said, a third of the project is going to be spent on the first step and 2/3 are going to be spent on the second step, because C is the big unknown. We had to develop a precise operational semantics. We had to develop all the tools that reason about it precisely. We had to do a refinement framework that goes from a specification down to C and so on and so forth. And it turns out, because we used Haskell and because this was a program proof already, because all the data structures are laid out already just the way we wanted them in C, and that's the way kernel programmers think. So even when they use Haskell, they think about the bits and bytes and how you lay them out in memory and which bits of the page table data structure you can abuse for storing other information as well, and so forth. So that's all already in the Haskell prototype. So when implementing the C, first of all, it took almost no time. It took about 2 weeks to write down the first version of the C implementation. It took another 2 months to actually get it running. So the debugging of a microkernel is really hairy, because there's no device driver or a debugger or something that can tell you. You start the thing, you boot it up, you have a blank screen, nothing happens. Now you can start to think. Why is that the case? So they got around that, and it just works fine now. And yeah, so the main thing here is that the deep semantic reasoning was already done, and we basically could concentrate on modeling C and dealing with C and dealing with its pointers and all the not so safe features of it, proving that our use of them was safe. So And for any new properties that we needed on the C code, we were successfully able to shift the reasoning from the C code up to the Haskell level, on which we had already, well, not tens of thousands, but thousands of theorems available. So in the first refinement step, we had proved all these invariants, and we could use them now to derive further properties, basically. We didn't need to prove any new invariants at all, where we spent most of the effort in the last step on the C code. But we did, because of some optimizations in C, we did prove around 10 or so on the Haskell level that we then exploited to prove properties on C. Okay, so 160 bugs found and 54 further code changes that just made our life a bit easier, where we just said, if you do these two things in the other way around, then I don't have to prove that the first statement preserves the precondition of the second, for instance. Things like that, where there's just a trade-off between changing the kernel a bit, which preserves semantics, or sitting down and for, I don't know, a few days and proving that this transformation preserves semantics. So that's the kind of changes we did there. Okay, summary. Well, what we have in the end is a formal proof in Isabelle Hall, all the way from abstract down to a C implementation. So no assembly yet, but we could do that in the future. 7,500 lines of C actually proved in Isabelle. All in total, with libraries, frameworks, and so on, it's 200,000 lines of painfully manually written proof, but it's machine assisted and machine checked. There is actually quite a lot of automation in there. So there are tactics in there that state lemmas for you that recursively state the same kind of lemma for all functions that are called, and proves simple invariant properties for you just completely automatically without you doing anything. About 10,000 intermediate lemmas, and these 160 bucks are interesting because we gave the kernel, before it was verified, the C implementation, we gave it to students to do projects on, and we did some testing on it, not much because we were verifying it anyway. And that, well, I mean, we're supposed to find all of them, right? So that process of testing, end of running student projects for about 6 months, found 16 bugs. And a further 144 were found in the verification. That just, yeah, I don't know. I don't think it's quite the same factor in normal software because, as I said, we didn't do much testing. But I think a factor of 5 or so you might still find in normal software that is tested, as opposed to completely implementation proofed with respect to a functional specification. Summary of the Haskell influence. The main thing. I think for the success of this project was that we used Haskell as this interface between the OS designers and the formal methods team. Either team alone couldn't have done it, and this was really the interface where all the concepts were shared and everyone could talk about and had a common denominator. It supported very large proof, and because it had clean semantics, we could put it into Isabelle Hall. Thanks. That's it.
Questions?
So I'm interested in learning how many times you had to change the Haskell specification.
About 150 times as well.
As well, okay. And that was to make proofs easier, or because you found problems in the specification?
Okay, sorry, my answer was actually wrong. Changes were 300 times, 150 times were bugs, 150 times, roughly. We haven't counted that precisely in the Haskell one, were to make our life easier.
Okay.
Sometimes it's a bit, is it a feature or is it a bug or is it, unexpected behavior? But.
So you mentioned that you wrote the Haskell model in some monadic way. Was it because of implementation reasons, because there are libraries were constructed monadic, or was it because it is actually easier to prove the monadic code? I mean,
it was because it was easier to write, not necessarily to prove, although I think now that it was actually easier to prove as well.
Oh,
so the initial motivation was the OS guys, they didn't care much about the proof. They cared about writing down what their design is, and the simplest way to do that for them was using monads.
Oh, then you mean that, I mean, since it's a model, you can just write it as a big state and state transition without anything, but it's still writing as a monadic cell was actually easier to
Yes,
prove.
exactly. Yeah. Maybe one thing to add to Matthias's talk. The reason why the OS guys were keen on Haskell was because all of them had Haskell in first year at uni. And in the second year of this project, the uni decided to switch that to Java and C.
One more question.
So I think it would have been interesting to have tested the microkernel more extensively before starting the proof. And I'm naturally imagining that you might use QuickCheck to compare the behavior of the Haskell executable spec to the C code. I wonder whether that might perhaps have helped reduce the effort of the proof. After all, finding an error, finding a bug in a program by not completing a proof is quite an expensive way to find it. I can imagine that you may have needed to redo quite a bit of the proof after each change.
You don't actually, usually we didn't have to redo much because the program was usually right in spirit. It was just a typo or a simple error that is very easily fixed. So the turnaround time for this was about maybe, well, 2 hours, 2 to 4 hours to re-implement, change all the specs if the bug was in the specs as well, and rerun the proof up to that point. So a complete round trip in our proof takes about 4 hours for processing everything. If it's a debug, yes, then it might take longer, but that wasn't the usual case.
All right. Let's thank the speaker.